imagine that we're in 2 dimensions. Here's the set of all people who are buying the product. If we now change y, that's going to change the set of people who's buying the product to this, right? And what we need to add up is the value of the function over all these points where it changes, right? And the rate at which it changes is how fast this is moving at any point with respect to changing the variable. OK. So this is often called the extensive margin in economics. The extensive margin is who buys or does not buy the product, who does something or does not do it. So like imagine we were to change a tax. That would be like how many people are moving into and out of the labor force, right? And that's proportional to the rate at which people are attracted into the labor force and to how much money they earn. Say if we're saying what's the effect that that has on total tax receipts, it's the product of the number of people who are attracted into the labor force multiplied by how much taxes those people who are attracted into the labor force earn. OK. So the shorthand we're going to give for this, though it's not completely mathematically correct, and you can look at the paper if you want the details, is the integral along this boundary of this quantity. Now, the reason that that's not exactly correct, as you probably remember from calculus, is when you integrate along like a boundary, you have to sort of like take a line integral rather than an interior integral. But anyway, we'll just ignore that for now. OK, the second effect is the effect on the interior, right? And that's going to be the integral over the range that you're integrating in of the derivative of this h function inside with respect to y, right? And that's what we call the intensive margin. That's people who are already buying the product. How does the amount that they're purchasing change, right? So that would be like, rather than people who are getting into and out of the labor force, how much more or less do people who are already in the labor force work when we change taxes? OK. So to define this, we want to define the set of marginal consumers. These are the people who are just on the boundary, who are just indifferent to buying the product or not. That's the set of all types who have a utility that's exactly equal to price. Sorry, not 0. There should be price here. And that contrasts to the set of all people who are already buying the product. Right? OK. So let's try applying Leibniz's rule to taking the derivative of the number of people who are buying the product with respect to the price. So Andy, where's Andy? Yeah, Andy, how would we do that? So we want to decompose the derivative of this n here, which is an integral. We want to figure out what it is when we change this price here.
So it's dn with respect to p?
Yeah. So Leibniz's rule says there's 2 effects, one on the interior and one on the boundary. First, let's look at the interior effect. Is there any effect there?
I don't think so.
Yeah, because there's no direct dependence of this on p.
Right.
Right?
Right.
So again, we're saying how many people are buying the product if how many people buy the product is not affected directly by the price, only by changes in who's purchasing the product or not,
so
right?
We have the marginal, the inframarginal?
Yeah, so we want to figure out the extensive effect. Okay. So what is that? That, we said, was the derivative of this function that determines what the boundary is with respect to p.
Right.
So what would that be?
So that would just be the negative of
yeah.
the integral of
over what set?
Over C theta?
Yeah, over the boundary. Exactly right. Because we can re-express, we can move this p to the other side of this equation, and then we just get -1, and we integrate that on the boundary set, the set where this is equal to 0. Right? OK. And I'm going to denote the set of people, the number of people who are on the boundary as m, that density integrated over the boundary. OK. I'm going to measure things in terms of the fraction of people who choose to buy the product. N is going to be the fraction of people who choose to buy the product. And the firm is going to make profits, which are equal to the price times the fraction of people who buy the product, minus the cost, which depends on the number of people who buy it and the level of the non-price instrument. This should be N here, by the way. So the optimal price is still going to be given by the same formula we had before, which is going to be price minus the number of people buying the product divided by the number of people who are just indifferent to buying the product or not. That's the equivalent of before P prime, which is 1 over Q prime, times N. Right? OK. And you're going to set that equal to marginal cost, which here is the derivative of cost with respect to the number of people. So that gives us the optimal price. But now we want to figure out what's the optimal setting of the non-price instrument rho. OK. So first, I want to try to figure out what would be the socially optimal level of rho to set. Well, socially optimal means that we want to maximize the difference between the utility that people get in total and the cost of providing that utility. Right? The utility people get is the integral over all the people who are purchasing of their utility minus the cost of buying it. Right? And I want to try optimizing this while holding fixed the number of people who are buying the product. Why is that? Well, we've been discussing the distortion that a monopolist gives by reducing the number of people who buy the product. So we've sort of already handled that part, right? So I now want to leave that aside and say, holding fixed the number of people and that distortion, how much does he distort the level of the non-price instrument, right? OK. So what I want to do is figure out what's the derivative of this thing if I hold fixed not the price, but the number of people who buy the product. Now, how could we hold fixed the number of people who buy the product? How much would the price have to adjust in order to hold fixed the number of people who buy the product? Charlie, can you explain how we could figure that out? I see. So we want, OK, if we change the non-price instrument, right, that's going to change the number of people who buy the product, right? But if we change the price, that also changes the number of people who buy the product, right? And so we need to have the price adjust when we change the non-price instrument so as to offset the direct effect of changing the non-price instrument on the number of people. Do you know how we would solve for the rate at which the price has to change?
You would then just set it equal to the effect of changing the quality component?
Yeah. So how would you do that? What equation would you write down?
Would you set the boundary effect equal to the interior effect?
Not quite. Does anyone else have an idea? David?
Is this, if I'm following correctly, is this like an elasticity kind of? Because you're setting one kind of dependent on the other and measuring how much that changes?
Yeah, it's related to that.
Okay.
But you need to write out an equation for it. Does anyone have an idea what equation? Yeah, Connor?
Do you take the partial derivative of the profit with respect to the change in that?
Well, it's not profit here, right? We want to keep the number of people fixed, right?
Oh, is it an n?
Yeah. So you take the partial derivative with respect to what?
The instrument.
The instrument, and then what else?
You set it equal to change in n with respect to the price?
Yeah, that's basically right. So you want to say that we want the total effect of changing the non-price instrument on n to be 0, right? And that has two components by the chain rule, right? It's got one which is the direct effect, and then it's got one which is an indirect effect from the change in the price, right? And we want to set the sum of those two effects to 0, right? So what do we do? Well, the effect of changing the price on the number of people we said was negative m times this thing we were going to solve for, which is how much does the price have to change when we change the non-price instrument. And then we have to add to that the direct effect of changing the non-price instrument on the number of people, which we can derive from Leibniz's rule again, right? Because the number of people, remember, the interior has no direct dependence, right? And the boundary, what's the effect we get there? Well, what's the derivative of the boundary with respect to a change in the non-price instrument? It's the marginal utility that people get from that non-price instrument. And we're going to integrate that times the number of people around the boundary, right? Because that's the rate at which people are attracted in multiplied by the number of people that are attracted in, right? OK, so that gives us an equation. That's equal to 0. So now let's solve that out. Now to do that, I want to define an expectations operator, a notion of averaging. So if something's going to be average along the marginal set of marginal consumers, what we're going to call that is the integral of something multiplied by the number of people divided by the number of people, right? That's the usual notion of an average. When we add up the value of something times how many people are like that divided by the number of people that there are, right? OK, so then we can express this as just being the number of people who are on the boundary times their average marginal utility. And we get this equation here. If we then divide through by m and move this to the other side, we get that the amount that the price has to rise when we increase quality to hold fixed the number of people is the average marginal utility people get from quality. That's very intuitive, right? If I want to hold fixed the number of people, the price is going to have to rise in line with the average value that people put on quality to keep people from entering or exiting, right? OK. So, Lewis, how can we take the derivative now of this up here with respect to the quality while holding fixed the number of people that buy the product?
Not really sure.
Does anyone else want to try, or should I just go through and do it? OK. The key point is that the number of people is being held fixed, right? That means, and all the people that are coming into and out of the market have a utility which is exactly equal to price. They're all marginal, right? So anything that's happening along the boundary has to wash out, right? Because we're gaining and losing some people along the boundary, but all of them have a utility that's equal to price. And we're gaining and losing an equal number, right? Because we're holding fixed the number of people. So any effect through the boundary of this thing disappears. And so the only effect we get is on the interior, which is the integral over the set of people who are buying the product of their marginal utility, minus the marginal cost of providing a non-price instrument. And so the derivative is the number of people times the average marginal utility of all the people who are buying the product minus the cost of providing it. OK. So